Section 30 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler, Astronomy. Chapter 20, Comets, Meteors, and Meteorites, Part 3. Meteors, often called shooting stars, which is some instances at least, must be the remains of comets, are small solid bodies which revolve around the Sun, generally in great numbers, following approximately the same orbit, and are encountered by the Earth in its annual revolution. Then they graze the Earth or even fall toward it, but fortunately for its inhabitants they seldom reach its solid surface, because they are raised to incandescence and dissipated in vapor by the heat generated by friction in their swift rush through the atmosphere. At certain seasons of the year the Earth traverses comparatively dense swarms of meteors and is subjected to a veritable bombardment. The effect to the eye of these flashing meteors is most striking and brilliant, particularly if the point of the swarm, intersected, contains a large aggregation of meteors. The apparent radiation of a meteoric shower from a common point, or radiant, is an effect of perspective, as the meteors of a swarm in reality pursue parallel paths. 3 of these meteor swarms are of particular interest, as under certain conditions they give rise to fine displays. They are known as the Bielids, the Leonids, and the Perseids, the first occurring in November and the last named in August. The Bielids, deriving their name from the connection of their orbit with that of the comet Biela, are also known as the Andromedids on account of their apparent source in the constellation of Andromeda. M. Egenitis, director of the observatory at Athens, traced back the Andromedid shower to the times of the Emperor Justinian. Theophanes, the chronicler of that epoch, writing of the famous revolt of Nika in the year 532 A.D., says, "During the same year a great fall of stars came from the evening till the dawn." M. Egenitis notes another early reference to these meteors in 752 A.D., during the reign of the Eastern Emperor Constantine Copronymus. Writing of that year, Nicephorus, a patriarch of Constantinople, states, "All the stars appeared to be detached from the sky and to fall upon the Earth." But it was not until the 19th century that the Bielids aroused much attention, and then it was in great part due to the fact that apparently the same orbit was occupied by them as by Biela's comet, which we have seen was not observed after its appearance in 1852. The Bielid shower, however, since that time has shown increased activity, which was especially true in the years in which the comet, were it in existence, would have been scheduled to pass near the Earth. In the case of the Leonids, records of their occurrence go back as far as 902 A.D., which is called Year of Stars, because on the night of October 12th, while the Moorish Ibn Ben Ahmed was dying before Cosenza in Calabria, a multitude of falling stars scattered themselves across the sky like rain, and naturally aroused great excitement among those who beheld the phenomenon, which they considered a celestial portent of unusual significance. In 1698 modern history of the Leonids began. A maximum Leonid shower has occurred with considerable regularity at periods of about 33 years from that date. In 1799, on the 11th of November, Humboldt and Bonpland witnessed a notable display in South America. On November 12, 1833, meteors were said to have fallen as thickly as snowflakes. In 7 hours 240,000 were estimated to have appeared. The radiant from which meteors seemed to come was found to be situated in the head of the constellation of Leo, from which circumstance the name of Leonids results. Professor Denison Olmsted of Yale University assigned to this cloud of cosmical particles the path of a narrow ellipse in an orbit around the Sun and intersecting that of the Earth. This marked the beginning of an important department of astronomy. In 1837 Olbers established the periodicity of the maximum shower, which indicated a regular distribution of the meteoric supply. In 1866, as conjectured by Olbers, another time of maximum occurrence took place, which seemed to demonstrate that while the Earth cut through the orbit each year, about the same date, at the 33-year period the swarm was at a point of maximum density in the orbit. In 1899, however, much disappointment was caused by the failure of the Leonid shower to take place on the scheduled date. a failure which was explained as due to the attraction of one of the larger planets which had diverted the orbit from its old position so that the Earth failed to pass through the swarm. The cometary connection in the case of the Leonids is shown by the fact that they seem to travel in the orbit of Tempel's comet of 1866. The Perseids date back to the year 811 a.d. and derive their name from the constellation of Perseus, where the radiant point is situated. They are seen on the 10th of August in continental Europe. As this is the day of St. Lawrence, they are known as the Tears of St. Lawrence. But this date is not the only one on which meteors from this swarm are to be observed, for they fall in greater or less numbers from about July 8th to August 22nd. They are very rapid in their motion, and the trails often persist for a minute or two before they are disseminated. The Perseids have an easterly motion, shifting each night by a small amount. Their orbit cuts the orbit of the Earth almost perpendicularly, and they are supposed to be the debris of an ancient comet which traveled the same path. Various comets, especially that of Tuttle in 1862, seem to have had the same orbit, and the meteors are quite evenly distributed along the path. There are other swarms of meteors, such as the Lyrids, the Orionids, etc., and Mr. W. F. Denning of England, who has made a specialty of this field, has accounted for 3,000 other less conspicuous showers. Astronomers have shown that the various meteor swarms and comets move in the same orbits. Accordingly, the theory has been proposed that when a comet is captured by a planet, the material of the tail is driven off into space, and the remaining material, disintegrated by the various forces at work, is distributed along the orbit. Consequently, the phenomenon of a meteoric shower occurs when the orbit of a swarm and that of the Earth intersect, and when the Earth and the meteors arrive at this intersection at the same time. Leverrier showed that the Leonids resulted from the capture of a parent comet in 126 a.d. at the time of a near approach, and that the disintegration, not entirely completed, is already far advanced. He claimed that the Perseids were of much older formation. Meteors have been observed from the earliest days, but are of such minor importance as compared with comets that they attracted no particular attention. In 1719, Brandes and Benzenberg, at Göttingen, by making simultaneous observations of the beginning and end of the path of a meteor from different stations a few miles apart, were able to determine not only its position but its velocity, and subsequent observations similarly made indicate that meteors appear at altitudes of 60 to 100 miles and that they move over paths of 40 or 50 miles, traveling at a rate of 10 to 40 miles per second. When a meteor enters the Earth's atmosphere from interplanetary space, the friction of the atmosphere, caused by its high velocity, develops heat and causes it to shed a brilliant light. The temperature of a meteor rises to many thousand degrees centigrade, and for that reason it is usually consumed before it reaches the Earth's surface. The products of oxidation and disintegration consist simply of dust, which falls on the Earth's surface or is distributed throughout space. In the main, meteors simply contribute dust to the Earth. The energy of the meteor as well as its mass can readily be ascertained if its distance, the duration of its luminosity, and its brightness are known, for the total amount of light radiated can be calculated on the basis that its entire energy is thus transformed. The mass of a meteor is not particularly large and is usually but a small fraction of an ounce. For the most part it is not larger than a pea or pebble. It is the atmosphere that not only heats these rapidly moving bodies but acts as a protection to the Earth, for if meteors were not thus disintegrated they would fall upon its surface in a constant bombardment. In addition to the meteors seen with the naked eye, estimated by the late Professor Simon Newcomb at not less than 146 billion per annum, there are doubtless 10 times as many which pass merely as streaks of light in the field of the observer's telescope. In addition to the extremely fine dust which settles on the Earth as the result of disintegration of various celestial bodies, there are from time to time masses of greater or less size which, rushing into the Earth's atmosphere with a brilliant glow due to the heat generated by friction, fall to the Earth's surface and become more or less embedded. The appearance is most striking, accompanied as it often is by a loud roar like a waterfall and occasionally violent explosions. Thus it is stated that at Cairo in August 1029 many stars passed with a great noise and a brilliant light. These bodies, a number of which come to the Earth's surface yearly, are termed meteorites, siderites, uranoliths, or aerolites, and apparently are the connecting links between the Earth and outside space. Their nature is none too well known and they present many unsolved problems. It is interesting to know that the great Mexican meteorites at the time of the Spanish invasion were considered holy bodies by the Indians, so that it is inferred that their fall from the heavens was known and was regarded as a supernatural occurrence. In the Greek and Roman records similar attention was paid to the Palladium of Troy, to the image of Diana at Ephesus, and to the sacred shield of Numa, all of which were said to have fallen from the heavens and were no doubt meteorites. Meteorites are usually divided into two classes, those composed chiefly of iron and those composed chiefly of stone. Of the 292 actually observed meteoric falls that took place during the last century, only 12, or about 4%, belonged to the first class. Yet in our cabinets the two classes are represented in nearly equal numbers. The explanation of this strange anomaly lies in the fact that unless the fall has actually been witnessed close at hand, very few of the stony meteorites are ever found. Of 328 in the collection in the British Museum, 305, or 93%, were seen to fall. This is partly because these bodies to ordinary inspection appear very like common stones, and therefore are not recognized as meteorites, and partly because, owing to their physical and chemical structure, they are readily decomposed by the action of the elements. It is the custom to associate meteorites with falling stars, and to say therefore that they are of cometary origin. This relationship, however, is not as obvious, when we begin to examine into the case, as at first sight appears. A prominent difficulty is that the distribution of the meteorites throughout the year differs very materially from that of the falling stars and fireballs. While the last two are about twice as numerous during the latter half of the year as during the first half, the meteorites are more numerous during the first half of the year. From this we should infer that while perhaps all meteorites are fireballs, only comparatively few fireballs become meteorites. The dividing line between meteorites and falling stars then lies among the fireballs, the swiftly moving ones being allied to the falling stars and the slowly moving ones to the meteorites. It is now generally accepted that the crystalline and often conglomerate structure of these bodies proves them to be but the fragments of much larger bodies that have in some manner been destroyed, or from which they have otherwise become separated. Many believe that the crystalline structure of the iron meteorites indicates a slow cooling, while some say that the structures of the chondrules of the stony meteorites must certainly have been produced by a very rapid crystallization due to a sudden exposure to a lower temperature. It was formerly thought by some that these bodies might have been expelled from the Sun. Although it is quite possible that solar explosions in past ages were sufficiently violent to project these bodies with the necessary cometary velocities, yet we cannot believe the Sun to be the direct source of them, since it is improbable that either solid stone or iron should ever have existed upon its surface or within its interior. Nor is it easy to explain how with such an origin the meteorites should have acquired their present orbits. Some of the earlier cosmogonists refer their origin to the terrestrial or lunar volcanoes. This is manifestly impossible in the case of the Earth, since even prehistoric volcanoes could not have expelled their products with such force that after leaving the confines of our atmosphere they should still retain a velocity of over 7 miles per second. Yet this is the speed required to prevent an immediate return to Earth's surface. Moreover, although volcanic eruptions in the prehistoric times were undoubtedly more frequent and voluminous than at present, it is by no means certain for theoretical reasons that they were then any more violent than they are today. Meteors escaping from lunar volcanoes would not have to encounter a dense atmosphere, and furthermore their required parabolic velocity would be appreciably less. But even under the most favorable circumstances, in order to escape both the Moon and Earth, a speed of over 2 miles per second would be required. That attained, they would then be controlled by the Sun and might be picked up at any later time by our planet in its orbit. The objection to this explanation is that no explosive volcanoes have ever been detected upon the Moon, all the craters being the engulfment type. It is therefore very improbable that such extremely violent explosions could have occurred there. While, as we have seen, meteorites cannot be the product of terrestrial volcanoes, yet it is suggested by Professor W.H. Pickering that the stony ones were all of them formed during the great cataclysm that occurred at the time that the Moon separated from the Earth. When the truly enormous pressure on the deep-lying terrestrial strata was suddenly relieved by the departure of the upper layers which now form our Moon, tremendous explosive energy must have been generated. Considerable portions of our atmosphere must have followed the larger flying masses, and the atmospheric resistance to the smaller ones, swept along at the same time, would have been much diminished. Although we can probably never definitely know just what occurred at this time, it is quite possible that considerable quantities of the smaller masses were carried along by the blast of escaping gases and were projected to such distances as to free themselves entirely from the attraction of our planet. This implies a solid crust for the Earth at the date of birth of the Moon, which previous investigations of the place of origin of that body seem to justify. In support of this view of the terrestrial origin of meteorites, we have the fact that 29 terrestrial elements, including helium, have so far been recognized in them, 10 of them being non-metallic. No new elements have been found. The 6 which occur most frequently in the Earth's crust, named in the order of their abundance, are oxygen, silicon, aluminum, iron, calcium, and magnesium. The 8 most commonly found in the stony meteorites are these 6, besides nickel and sulfur. Nearly all the stony meteorites contain some metallic iron, and some of them contain large quantities of it. But this is also true of some of our basaltic lavas. Indeed, large masses of iron have been found in ledges upon the Greenland coast. Some of this iron contains over 6% of nickel, but much larger proportions have been discovered in New Zealand, Piedmont, and Oregon, where considerable quantities of the nickel iron alloys have been found. According to Farrington, of the 21 minerals recognized in meteorites, 14 have been found in our volcanic products. It appears to Professor Pickering that the iron and stony meteorites differ from one another in other ways beside their composition. That some of the former are associated with falling stars, and therefore with comets, certainly seems plausible. That the latter are not associated with them seems probable, and if so, whence can they have come if not from our own Earth? End of section 30.